All right, everyone, today we are talking about motion, and that's particle motion, which covers velocity and acceleration problems related to FRQs. So we will start with the 2016 FRQ. This was number 2, which means it was a calculator active question that year. Now, these do sometimes come out calculator active, and sometimes they're non-calculator as well, but we often see them in FRQs. We don't always see them, but we see them enough to talk about them. Okay, so let's start by talking about the calculator active 2016 FRQ, and we like this one because it was just a fun question. All right, so let's dive in here. It says for t is greater than or equals to 0, a particle moves along the x-axis. The velocity of the particle at time t is given by v of t, and the particle is at position x equals 2 at a time of 4. So this is important because this is the position, and so I can go ahead and say this is x of 4 equals to 2. So that's important. All right, so I'm going to write that down. Now, at a time of 4, is this particle speeding up or slowing down? Now, we should recall that a particle is speeding up when the acceleration and when the velocity have the same sign. And since we know here that the time is 4, all we have to do is start taking the velocity of the function here at a time of 4, and I want to compare its value, and I also want to take its acceleration, or maybe I want to call that v prime of 4, right? Keep in mind, this is, of course, the acceleration, but at 4. Okay, so let's think about that for a minute. Let's go into our calculator. Let's go into our calculator, and let's put in our function, right? Okay, so our function was 1 plus 2, then we got our sign here, and we're going to create this fraction because it's nicer that way, and that's t squared over 2. I'm going to close this up, double check my function, looks great, awesome. Okay, now again, that's just a velocity, right? But I want to take this and I just want to plug in 4, right? So I could just quickly go into the table here, and I could plug in 4, and just like that I get 2.978. All right, so let me write that number down. 2.978. All right, now I'm going to take the acceleration at 4. Now, what does that mean? Well, that just means it's the derivative of the velocity, right? So I'm just going to go in here and go math 8. That's our derivative of the function that we have in the calculator, which is currently under y1, and I want to plug this in at x equals 4. All right, and I get here negative 1.164. So negative 1.164 right there. Now, the particle speeds up when these things have the same sign, and right now I'm looking at them, and they have different signs. So the question is the particle speeding up or slowing down at t equals 4? So let me summarize here and just say the particle is slowing down at t equals 4 because v of 4 is greater than 0 and v prime of 4 is less than 0. Or, if you want, you could even say because the velocity and the acceleration have different signs. Okay, so here's that answer, nice and neat, written down. So again, you can say because v of 4 is greater than 0 and v prime of 4 is less than 0, or you can write this down more verbally and just say the particle is slowing down at t equals 4 because the velocity and acceleration have different signs. Okay, so let's move on to part B. Find all the times on the interval from 0 to 3 when the particle changes directions. Well, that happens when the velocity changes signs. We might want to start by looking at when that velocity then is perhaps equals to 0. So that's a good place to start. So we have that velocity function already in the calculator, right? Let's see, we want only the values t is greater than 0. So let me go to window here, and I'm just going to go ahead and put 0 for my x minimum, and let's just take a look. Whoa, all right. So we want to know from 0 to 3, perhaps. I can reduce that down some more, right? Oh, I missed that the first time. So maybe from 0 to 3. Let's not do that again. And when we hit graph now, we're looking at it way more specific. So this is the interval from 0 to 3. And I want to look at when it changes signs. Well, right now, this velocity is positive because it's a positive y value. and then all of a sudden it's a negative 1. When does that happen? When does it change signs? It happens right there. What do we call that point? That's called a 0, right? Because it's an x-intercept. So we're going to calculate a 0, and we're just going to select the left bound. Now we got to hover all the way to the right, so we can go some point on the right of that 0, which I guess this is good, right? And somewhere in between these two lines that I created, these boundaries if you will, that's the 0. There it is, okay? So the 0, also known as the critical point here, is a 2.707. Let's write that down, okay? So then the t-value here would be 2.707, okay? Now, could we perhaps show this a little nicer? Yeah, I mean, if you wanted to make a sign chart, you can go from 0 to 3. You discovered then that this is 2.707. Maybe you want to verify this. Could you maybe plug in a number into your velocity, something between 0 and 3? Sure, like if you were to plug in 1, you'd probably see that you get, here's 1, right? You'd probably get a positive number. Well, if you plug in something that's negative, but after 2.7, maybe like 2.9, you'd probably get a negative number. Okay, so that's really what a sign chart does. Here we're just looking at it more graphically. And anyway, particle changes directions at t equals 2.707. Now, a lot of the times you're asked here to justify. So why? Why is that our answer? Well, it's because the velocity changes signs. A particle changes directions at t equals 2.707 because v of t changes from positive to negative. That's a little bit more specific. Okay, so let's talk about the point breakdown, right? So that's already 2 parts here of the question. So far, we've only really messed with derivatives, right? So in the last part of the question, we had to kind of figure out, hey, what's the velocity at 4? What's the acceleration at 4, right? And so for this part of the question, this was worth 2 points. 2 points for the conclusion that, of course, was tied to a reason, okay? So conclusion with the reason, all right? In this part of the question, question B, also worth 2 points, okay? 1 point if you can get to this t-value right here of 2.707. That's a critical point. And, of course, another point here for the justification, okay? So that's pretty important. So far we got 4 points, and the reason why I talk about it at this time is because that's the half C's mark, right? We want to get to 4 or more on the FRQ. So that's how we can get there, the easy and the fastest way. All right, so let's look at question C. Question C says to find the position of the particle at a time of 0. Find the position of the particle at a time of 0. Well, that's crazy because all we have right now is a velocity. So how do we go from velocity to position? The integral, right? Very good. And so that's exactly what we're going to do. But remember, we are given an initial value right here. I just didn't write it on this side. This is x of 4, which is equals to 2. We can use that concept here. It's basically just an integral. But let's use that, right? So we want to find the position of the particle at a time of 0. So that's basically, hey, find x of 0. Oh, no big deal. Well, I know that x of 4 is like an initial value. So I can take my initial value here, my x of 4, and then I can add the integral that goes from 4 to whatever, right? Usually we'll say like x. Well, in this case, we're going to put 0, and this is the derivative, right? A v of t dt. Okay? So we can start by doing that right here. And students that can write out this integral actually get the first point right there. Okay, so I'm going to write here, this integral. Students that can write that down, and you actually have to do this on the graphical analysis FRQ, so you're actually using this skill here as well. All right, this is going to be pretty helpful. All right, so anyway, we know that x of 4, we know that that's 2. That's like an initial value. And then the question here is, well, wait a second, this is backwards, right? I can swap this around and rewrite this so that it's really minus, and then from 0 to 4, v of t dt. Right? And so that's x of 0 so far. Well, we use our calculator here, so let's open that up. See, I'm just going to move this over a little bit. Okay. Maybe a little more. There we go. Okay, so I want to put into that home screen, I want to put a 2 minus, and then I'm just going to go ahead and hit math 9, so I can go from 0 to 4, and then my velocity function, which is of course that guy, right, y1, and I want to put here, dx. Alright, so when I hit enter, you'll notice that we get negative 3.815. Let's write that down. And so we got 1 point here for the integral. Let's analyze this in a minute. We got 1 point also for uses of the initial condition. Oops. And then the last point will come from the answer here. So that's not too bad. That's 3 extra points, and it's all calculator active. Okay? So integral, initial condition, and answer. Look at that, 7 points so far. We're missing 2, right? Okay, so part D. Let's do that one. And so for part D, find the total distance of the particle travels from a time of 0 to a time of 3. Now, it's been a while since we've done distance, but you might remember that distance is really just the absolute value inside of that integral, okay? So we're just going to set this up to go from 0 to 3, absolute value v of t dt. And the nicest part about all this, it's calculator active, right? So it goes right up into the calculator, and this is going to be nice and quick. So math 9, we go from 0 to 3. We know we're going to put that velocity function, but first let's hit math, numbers. So you got to go to the right and select absolute value. So in there you can put your y1, all right, and then we go ahead and put dx there, and awesome. All right, imagine doing this on our own, right? So 5.301, you guys might remember that. 5.301. All right, so we're missing 2 points, so that's where the other 2 points come from, right? The good news is, oops, I keep forgetting the 1 here. 1 point if you can set up this integral, and 1 point if you can get to the answer. Okay, so calculators here are extremely helpful. All right, so that's 9 out of those 9 points. Not too bad, and again, this one was calculator active, right? So now, let's, oh, by the way, it took me 13 minutes to explain that to you. And you saw I put in everything in the calculator just like that. So now, let's find the other one in our packet here. That's 2017. I like that one also because that one is a non-calculator FRQ. You'll notice here it's listed as problem number 5. Okay, so for problem number 5 here, this time we have 2 particles moving along the x-axis, right, for a time of 0 and a time of 8. Now the position of particle P at the time t is given as x of P for particle P, and then of t, right? And then we got this function here, right? Keep in mind, this is not calculator active. While the velocity of the particle Q at another time is given here. So with one function, we're given the position. With another function, we're given the velocity. Oh my gosh. Particle Q is at position 5 when the time is 0. This is really an initial value that they're giving us here, okay? It's telling us particle Q. So I'm going to write it under this guy here. Particle Q is at position 5 at a time of 0. I know this looks kind of weird. This is a Q. But it's only because we have a Q and we have a P, okay? So extra fun, right? Ooh. These do come out a lot, by the way. The ones with the 2 particles, we've seen these a couple years, back to back sometimes. So just keep that in mind. Sometimes they're calculator active and sometimes they're not. From 0 to 8, when is particle P moving to the left? Now, we know that particle P is this guy here, which is the position function that was given. It's moving to the left whenever the first derivative is negative, right? So I can actually start that because these are typically going to require some sort of an explanation. So I can start by saying particle P moves left when the velocity is less than 0. Maybe I want to start by saying that, okay? And that way you already have your justification, okay? But either way, we need to take the derivative here, okay? And so if we were to take the derivative here of particle p, this would be vp of t, right? And then you might recall the derivative here of the ln function. It's just the derivative of the inside over all of this stuff right here, right? Okay, so it's going to be, and then of course 1 over that. So this is just going to be 2t minus 2 over, and then we got that t squared minus 2t plus 10. All right, so can we do anything to this? Well, we want to know when the particle is moving to the left. We want to know when this is in fact going to be negative. So if you want to know when your derivative is going to be negative, you first got to find your critical points, right? All right, so remember, this is a non-calculator question. So even though sign tables aren't part of a justification, they could be helpful for you to maybe find some work, right? Okay, so I'm just going to go ahead and put here from 0 to 8, and I maybe want to find any critical points. So critical points is whenever your derivative is 0, right? So in this case, that happens when the numerator is 0. So I'm just going to go ahead and say 0 is equals to 2t minus 2, right? And then if we move the 2 to the other side, let's see, this is 2 equals to 2t, so t equals to 1. Okay, so that's great. So we got a 1 here. All right, so from 0 to 1, I want to test something out here now, and I want to plug maybe like a 1/2 or something into my velocity function and see what I get, right? If I get a positive number, I know I'm putting a plus there. That means the particle is moving to the right, and then I maybe want to plug in another number this way and see what kind of sign I generate there, right? Okay, so this is going to be fun, right? So let's plug in into our velocity. Let's plug in like a 1/2 or something that's not too difficult to work with, right? So let's see, velocity, I guess we should put a p here, right, for particle p. Woo! Oh my gosh. There you go. Okay, velocity of particle p at 1/2. All right, what number is that going to be? Let's see. If we plug everything in here, let's see, we end up with a negative number. All right, so I'm going to go ahead and put a minus here. Okay, so here's a little scratch work for that 1/2 when we plug it in, and you can see the number is going to be negative, right? Again, if you don't want your reader to see all this, just scratch it out, okay? And then we're going to also plug in some number like 2, maybe, right? Something from 1 to 8. So pick something simple like 2, perhaps, right? And let's see, if we do 4 minus 2, that's just going to give us 2 up there, right? 2 squared is 4, 4 minus 4, and then plus 10. These cancel each other, but we're going to get a positive number. So this is a plus. So the question here is, hey, when is this particle moving to the left? Well, that happens from 0 to 1. Okay, so how can we write our answer? Well, we want to write that the particle P is moving to the left from a time of 0 to a time of 1. Well, what's happening at 1, though? At 1, isn't the velocity 0? Yes, right? And what does that mean? It means that the particle's not moving. Okay, so don't include 1 in your answer, please, okay? All right, so we're going to say here, there we go, 0 less than or equals to t, which is less than 1. You can also write it like that, okay? I usually like interval notation a little bit better, okay? All right, so let's look at part B here. Part B is asking us, part B is asking us from the time of 0 to 8 again, find all the times during which during the two particles travel in the same direction. In other words, when both particles are moving left or when both particles are moving right. Oh my goodness. So we're going to have to compare both sign charts, right? Now, keep in mind that from this one, 0 to 8, we had that value of 1, and we said this was negative and this was positive, right? Okay, so now we're going to do the same thing, except now we're going to consider particle Q. Well, the nice thing about particle Q is that we already know the velocity, right? So if we set that up, let me put here P, velocity of P. So now let's do the same thing from 0 to 8, but this one will be the velocity of Q. All right, so 0 to 8. And let's see what we got here. Are there any critical points? Well, is there any time when this velocity is 0? Look, the fact that I wrote that down means, hey, I probably want to put that in my work. Okay, so the velocity of particle Q, hey, when does that guy equals to 0, right? Because we already know. Sometimes they give us freebies for just writing this down. right? Okay, well, are there any factors of 15 that add up to negative 8? And yes, there are, right? So that gives us t minus 5 and t minus 3, which means that's when it equals to 0. So I get two t values, right? T equals 5 and t equals 3. They both happen to be on that interval, which is perfect. We'll consider both of them. So we'll put 3 in here, and we'll put 5 over here, and we'll just start plugging in some numbers right in there, right? Into that velocity to determine their signs. Okay, so when we do that, from 0 to 3, we get a positive. I'm just going to speed it up for you guys a little bit, okay? From 3 to 5, if we plug in a 4, we actually get a negative in there, okay? And from 5 to 8, keep it simple. Pick like 6 or something, okay? We end up with a positive here. So when are they traveling in the same direction? Well, particle Q right now is traveling to the right. This one's traveling left. From 3 to 5, this one's traveling to the left. Well, from 1 to 8, this one's traveling to the right. So maybe from like the 5 to the 8, they're both traveling to the right. You guys see that? And so that's something that I want to say, okay? So the thing here is that the sign chart is not going to be part of our work. That's why I put it up here and not on the bottom, nice and neat with everything else, okay? This question usually asks us to explain. It doesn't really say explain, but we always want to explain these motion questions, okay? We can say both particles move in the same direction. We said from 5 to 8. Is there any other intervals? Let's see. I know I circled that one, but one would be here. And, ooh, wait a second. We do actually have a little bit more. Because if 1 is this way, and that's where we know it's negative, from 1 to 3, it looks like it's positive over here. And 1 to 3 is in this range here. So 1 to 3 is also a good answer to go with that interval. Okay, so let's include that as well. All right, so we say both particles move in the same direction for the intervals 1 to 3 and 5 to 8, since the velocity of particle P has the same sign as the velocity of particle Q. So there's the answer nicely written. I rephrased it a little bit. Particles P and Q travel in the same direction on 1 to 3 and 5 to 8 because Vp of t and Vq of t have the same sign. And let's talk about the point breakdown here for a moment, because after 2 questions, it's a good time to do it. So in question A, let's see, this one was worth 2 points. 1 point for students that identified the velocity here of particle P. All right, so students that identified that derivative actually just got that first point right there, okay? So I'm going to write Vp of t, or of course that's x prime, right? The interval, if the students got that interval correct, that was the second point. All right, moving on to part B. Part B also worth 2 points, but there's some fine print here. So the interval right there, boom, boom, 1 to 3, 5 to 8, the interval is a point, and the explanation or the justification is 1 point, okay? So I'm going to write here interval, and I'm going to write +1 for the justification or explanation, right? Okay, there's a fine print here. It says, note, half credit if only one interval with analysis is correct. That's that special case we talked about. And if there's no analysis given, meaning if the student got the correct interval but no reasoning whatsoever, 0 points. You did all that for nothing, okay? So make sure you explain these, okay? Notice the question doesn't even ask you to justify. Position questions always ask to justify, okay? All right, or better said, always justify just to be safe. All right, let's move on to part C. Part C, find the acceleration of the particle Q. This guy here, we're taking the derivative, right? At a time of 2, and is that speed of the particle increasing, decreasing, or neither at t equals 2? All right, well, let's start by taking the derivative of that, which is, of course, its acceleration. So let me write AC of t. Well, not C, I'm sorry, Q. Ooh. AC of t. There I go again. AQ of t. All right. Woo. And, all right, derivative of that. That's just a power rule, right? 2t minus 8. All right. Now, what can I do here? It's asking, find the acceleration of the particle at a time of 2. Usually, if that's a whole sentence, a lot of the times, at the end of that sentence, that's the first point. So I'm going to go ahead and take 2 and plug that in. Well, what happens if I plug in 2? Isn't that just 2 times 2? Yeah, that's 4 minus 8. No need to simplify, but let's do it just for fun. And it's negative 4. Find the acceleration of the particle right there at time of 2. Okay, so that means the acceleration of particle Q at a time of 2 is negative 4. Hey, is this speed of the particle increasing or decreasing, or neither, at a time of 2? So if you recall, speed means that the velocity and the acceleration have to have the same sign. I know we did that somewhere, didn't we? Let's see, where did we do that? We did the velocity of particle Q here, right? And 2 falls right here in this interval, right there, okay? And we know that at 2, the velocity is positive. So I want to write that down. I want to write V particle Q of 2 is greater than 0. I just want to write that it's positive. Who cares what the number is, right? I also want to write that the number that we just got, AQ of 2, that's a negative number. So let me just write here that it's less than 0. The velocity and the acceleration have the same sign. That is when your particle is speeding up. But these are opposite signs, which means particle Q is slowing down at a time of 2. Well, this is interesting. Slowing down is a fancy, well, not so fancy. I guess this is more fancy, right? Slowing down is another way of saying that the speed is decreasing. Okay, so let's use the wording that we are given to answer this question. We'll say particle Q, or the speed of particle Q is decreasing at a time of 2. And then this is our justification. Okay, so let's write that. The speed of particle Q is decreasing at t equals 2, right? Maybe we just want to write because the velocity and the acceleration have opposite signs or have different signs. That'll work here. Okay, I'm going to read that to you. The speed of the particle Q is decreasing at time of 2 because the velocity and acceleration have different signs. Let's talk about the point breakdown on this one. Also worth 2 points, which means we're really going to fish for the last couple points here. 1 point if students were able to come up with this answer right there to be negative 4. So that's 1 point for that derivative, basically, right? And then 1 point for students understanding that the speed was decreasing with a legit reason. The reason has to be because the velocity and acceleration have different signs. You could, of course, put this again in your work, no problem there. Okay? All right, let's get to that last part here. The last part is part D, and you can see this is a lengthy FRQ, right? We've spent a lot of time on this one already. Part D, find the position of particle Q the first time it changes directions. Find the position of particle Q the first time it changes directions. Well, let's see. I know that we talked about the velocity of particle Q somewhere, so that tells me when it changes directions. Where did we do that? The first time particle Q changes directions, you might remember, was right over here at time of 3. Okay? So we're going to use that here to kind of help us answer this question. Whoops, I went too far down. Find the position of particle Q the first time it changes directions. That happens at a time of 3. Okay? So, since we're looking for the position of the particle, aren't we basically looking for position of particle Q at a time of 3? That's what we're looking for here, right? Okay, well, do we have any initial values with particle Q? And I actually wrote it way back here. Look, we haven't used this at all. Or at least I don't think we have. Particle Q is at a position of 5 when the time is 0. So now we finally get to use that piece of information that we almost missed. All right? So I'm going to go ahead and use that initial value here. That's, there you go. Put that initial value in place here. And I want to go plus the integral, which goes from 0, it has to leave from here, and go all the way to 3, the value that we're looking for, right? And so that's the integral from 0, the initial value, to 3, the end position, if you will. And then in here goes your velocity function, so v of t, okay, dt. All right, so all of this is non-calculator. This is an initial value. This was 5. Okay, this is what we're looking for. So plus, do we know the velocity from 0 to 3? Well, no, but we can probably find it, right? So we can probably find this because we know that the velocity function is t squared minus 8t plus 15. I'm just going to plug that in here. T squared minus 8t, I think I messed that up, I'm sorry. Minus 8t plus 15, yep. There we go. Okay, so, and then we'll plug in from 0 to 3. So we're going to be using the fundamental theorem of calculus here. Alright, so this is just a power rule, so this is going to be plus t cubed over 3 minus 8t squared over 2. Let's get rid of that, make it a 4, keep it simple. Alright. Okay, and then plus 15t. Now remember, this was the integral, so I'm going to take all of that right there, and I want to plug that in from 0 to 3. Okay, now, that 5 there is going to stay there for a while. Alright, so if I start by plugging in 3 everywhere here, 3 cubed, actually, you know what, let me leave some room, because the moment I use this fundamental theorem of calculus, there's no need to simplify it, right? I can just say this is 3 cubed, which, I mean, yeah, I know it's 27, minus, this is 4 times 3 squared, that's 9, plus 15, oh, I don't even want to think that hard, forget it, 15 times 3, right? I can do this, and then I can do minus, and then I start plugging in 0, 0, 0, oh my gosh, everything is just a 0. I can leave my answer like that. There's no need to simplify these, okay? So let's leave it like that. We're getting that point right there, okay? If you do simplify it, I believe you get 23 on this one. But let's talk about the points. Remember I told you we'd have to fish for the last couple points. So the antiderivative right here, that right there, that was 1 point, okay? The integral. Did students use this initial condition right here, this 5? All right, so I'm going to put here plus 1. And let's write initial condition. All right, and then the last part is the answer, which again, you can get either one of these. That's cool. And that was the last point here, okay? So you can see here, woof, if you do get one of these this year, I really hope for you that it's a calculator active one, because the non-calculator ones really eat up your time, okay? All right, so I hope that was helpful, and I hope it was informative.